Good morning, students. Today's topic is Gibbs sampling. In last few classes, we studied about restricted Boltzmann machine (RBM), and then MCMC, Markov chain Monte Carlo methods. Markov chain Monte Carlo methods. Gibbs sampling is another MCMC method. MCMC methods is to generate a probability distribution. The same functionality is performed by Gibbs sampling. It's about generating samples. And Gibbs sample construct Markov chain whose values converges at a particular distribution. We saw that how through random points MCMC approximate the values. Likewise, here Gibbs sampling also uh, generate distributions. And Gibbs sampling is a specific case of this algorithm known as Metropolis hashings algorithm. There is an algorithm called Metropolis hashing algorithms. Uh, Gibbs sampling is a specific case of that. For instance, here, if you consider this multivariate probability distribution, and if you would like to sample this, then you can use Gibbs sampling. This is the figure that illustrates a multivariate sample. We see here, this is P, probability of Y, this is probability of X, this is sampling of two variables X and Y. And multivariate probability distribution, it is a function of multiple variables. That is two-dimensional normal distribution. This is normal distribution. Whenever you have a bell-like curve, it is a normal distribution. Gibbs sampling is applicable when the joint distribution is not known explicitly. When we don't know the joint distribution means variable x and y occurring together. That is joint distribution. If we say that a student attended class X and Y, perhaps that he has a laptop, for instance. If you say that this, the probability of this is 0.4, that's 40%, then this is a case of joint distribution. And we also have a conditional distribution in which we say that X conditioned on Y. If there is a laptop, then student is attending the class. This is condition. All right. Then therefore here Gibbs sample, you can use Gibbs sample when joint distribution is not known explicitly or difficult to sample directly. But then it relies on this conditional distribution. This conditional distribution is about knowing the occurrence of an event given or condition on another event. When you know this, you can obtain the joint distribution through a Gibbs sampling algorithm. And this algorithm starts off by selecting an initial value for the random variable x and y. Consider that there are two random variables x and y, and there is some initial value chosen, and then sample from the conditional probability distribution of x given y. Based on the conditional probability x given y that is sampled, and y naught, which is equal to y naught, denoted as probability of x given y naught. In the next, the subsequent step, a new value of y conditioned on x1 is computed. New value of y conditioned on x1, and this process is repeated for every value. For every value, what you do is you find the probability of x occurring given y, and y occurring given x. All right. Look at here. This is the Gibbs sampling algorithm. Here initially y x naught and y naught are initialized with a random or a initial value, and then based on this initial value, this is computed next value of this. Then subsequently this value helps to compute this. So here we can see that we are sampling xj for j1 to n based on the condition of x given yj minus 1. If you are generating x1, then it would be x condition on y naught. All right, yj minus 1. X2 will be x1 or x condition on y1, and yj, this is sampled by y condition on xj. Okay, whatever is the value of j, y condition on x naught, y condition on x1, like this. And these are the um, posterior and conditional probability distribution. Posterior and conditional probability distribution. xy 1 over c e x square y square plus x square plus y square minus 8x minus 8y over 2. So this is joint probability, this is conditional probability, and gy contains the terms that don't include x, and gx contains those terms that don't include y. G of y e to the minus this. You just substitute the values of x and y and obtain this. And c is a normalizing constant. Um, Through this conditional probability distribution, we know that occurrence of a particular event, that value we use to obtain to generate the posterior distribution, and that is approximation of the distribution. Gibbs sampling performs that approximation of posterior distribution, like MCMC, Markov chain, Monte Carlo. The conditional probability are in fact normal distributions and can be rewritten as this. Okay, these are all normal distributions. So from statistics, we know that this normal distribution, uh, mu sigma, you generate, and then you put all the values and to obtain this conditional. And these equations of Gibbs sampling have been implemented in Python, NumPy, SciPy, Matplotlib, Pandas, Seaborn. These are the built-in libraries in Python. Importing all of that and then setting Seaborn. Seaborn is advanced version of Matplotlib. It is built on Matplotlib. It supports various advanced uh, visualization features. Assuming that C equal to 1 initially, you see that how it is done. np.exp, that E, this formula is there, no? This one. C is 1 into E to the power that you are modeling here, like this. And then a distribution is plotted through this linspace. It is a NumPy uh, function. And then using this contour F, you are plotting this function, visualizing. Here, if for mu and sigma, random variables x and y are initialized, and n, the total number of iterations are set, and n is this 50,000. X is initializing to all zeros. NP is NumPy. Um, we are importing NumPy as NP, so calling that function zeros, zeros, and then x 0, first value, 1 point, means these are floating values. This is 6 point. Some values you are initializing. So apparently this is nothing but the sigma and mu, this implementation of those formulas that we uh, saw just now. And then this Gibbs sampling algorithm is iterated for I in range 1 to n. N is 50,000. Okay, so with a uh, skip of 2. So this that algorithm is iterated for 50,000 times. Finally, this plot is generated. This is nothing but the posterior distribution. This is all about Gibbs sampling, which is based on which is a variant of MCMC, which generates and approximates the posterior sampling or posterior distribution through conditional probabilities. Do you have any doubt in this? Next is the topic of this training restricted Boltzmann machine. There's a good article on this training restricted Boltzmann machine. That algorithm is known as contrastive divergence algorithm. RBM, restricted Boltzmann machine, has got two layers, visible layer and hidden layer. Visible layer is also known as input layer. This there are connections between visible layer and hidden layer. Like these are the nodes in this visible layer. These are the nodes in hidden layer, and these are connected. And here, how this training is performed in RBM is the topic of discussion now. This training occurs in forward and backward pass. forward pass, backward pass. During forward pass, the input is encoded in some form, some numeric form, and that form is uh, decoded back into input form, and later, if input actual input and generated input from encoded form are matching, it means that the RBM has learned the representation. Otherwise, this process continues until it converges. That is what we will study now, the steps of contrastive divergence algorithm for restricted Boltzmann machine. And RPM contains latent variables. Latent variables are those that occur in this hidden layer, and we need to add them to the probability distribution and log likelihood function so that we can properly decode them into this input form. And RBM uses energy function. This learning process of RBM based on the uh, concept of energy means there is a equation. That equation determines the process of this training. RBMs also uses likelihood function and its derivatives. Means what is the likelihood that in probability we know we put the likelihood that the likelihood of occurrence of this event X is some 20%. And then finally contrastive divergence algorithm, and then relationship with modern algorithms. There are some modern algorithms that performs the similar functionality, and that will be discussed towards the end. Latent variable model. If we have to capture the dependencies between visible features of restricted Boltzmann machine, which are the input, and hidden variables, which occur in hidden layers. So to capture this dependencies, we need to have latent variables. Look at here, this probability of X and H. This H nothing but hidden layer, hidden variable. And for this H is total number of hidden variables. Probability of X is the input. So what is the P of X is nothing but the sum of P of X with every hidden, because here every node in the visible layer is connected to every other node in the hidden layer. So this and this connection plus this and this connection. So this is summation of every for every hidden. All right, that gives this one this probability. Likewise, we do for this one and this one. And in energy-based model for Gibbs distribution, the equivalent form of this is this energy function P of X 1 over Z. Z is the partition function, which is equal to sum of exponent uh, minus E xh with all possible x and h. All possible of x and h combination means exponent. It is taking the power e to the power of minus e x, and you do this sum over all the combinations, this node with these two nodes, this one with these two nodes. This is known as the energy function, energy based model. And likelihood, whenever a model parameter is associated, the likelihood of hidden variable is computed by means of this equation. In this equation, what is the likelihood that a particular parameter theta occurs? Okay, this is ln natural log 1 over z. Then this one is this energy function. Then this, which is equal to this log of summation of exponent of xh. X and h are input and hidden nodes combination, all possible combination, minus log of natural log of summation of xh exp exponent. So this is this log likelihood of latent variable. Derivative of the log likelihood. This is the math behind deriving this equation. Derivative, finding the derivative of this equation. To find the derivative of this equation through calculates, we get this equation, and then this Bayesian rule. This is the Bayesian rule. Then the final derivative form of the log likelihood is this one. Definition of energy function is quite essential for RBM, and derivation of h comma x comma h. This e of x comma h for every possible input and hidden value, you have to compute the derivative and also define the energy function. And this is the energy function of RBM, restricted Boltzmann machine. You see here, this is sum over J1 to M, I1 to N. This is J input, I hidden nodes. You have to take every possible combination, right? And there are weights also associated. Every connection carries a weight. Every connection between this nodes in the visible layer and nodes in the hidden layer. Here you have weight W. This X, this H, and total number of H is M. J equal to 1 to M, and total number of X, I equal to 1 to N. All right, and this weight. So Xi H okay X J, okay, I'm sorry, J this M is with respect to input, N is with respect to hidden nodes. Okay, so with respect to uh, J and HI, so this will be W between this IJ, and this one will be J is different. No, J is same. Sorry, J is same. H is different. I is different. Here I will be 1. Here I will be 2. And this will be equal to Wij, which is nothing but uh, 2 1. This is 1 1. Ij. This is 1 1. This is 2 1. All right. This is that part. And then there is a bias. uh, that is being added, and then there is this bias of this hidden nodes, which is denoted as C constant. Every x is multiplied with b, every b, and take the sum of all. Every h is multiplied with c. Here there is another value. Okay, this c and this is b. So x and b and x multiply and take sum. C and h multiply and take sum. Add both and add this x and h uh, with its weights and generate the energy of this x and h. Likewise, for every x and h pair, this energy is computed. And eventually, you get an energy function for the model. When you do for all, you get the energy for this. Okay. And here, please recall that there is no intra-node connection within a layer. There are only internodes connection between the layers, but not within the layers. And that is a primary property of RBM. And then latent variables are conditionally independent given input features and vice versa. Latent variables, those that occur in these hidden layers, those are latent variables. They are independent given input features. So this is probability of H latent variable conditioned on H. Multiply with multiply for all I1 to n. This is H condition on X and this is X condition on H. Taking the derivative. Here derivative is calculated through calculus, and finally this term is obtained. This is the quantity that is obtained, which is the derivative of the above equation. Okay, and this is the log likelihood derivative. Because during backpropagation, during learning process, derivatives are pretty essential. Therefore, derivatives have to be computed. And this algorithms for training RBM model approximate the second expectation term in equation. In probability and statistics, you know that there is a first expectation term, second expectation term. So here, you through second expectation term, algorithms train RBM, and the algorithm, one of the algorithms is contrastive divergence, which is a standard way to train RBM model. And what it does is, the idea is running case steps. There are case steps, Gibbs sampling. So here, uh, RBM training essentially utilizes Gibbs sampling. What is Gibbs sampling? Gibbs sampling approximate the posterior probability distribution. That distribution is approximated in this RBM through this case steps until convergence. Convergence is the point where There is no further improvement. Excuse me, 1 minute. Okay, sorry about that. Um, okay, here the what is the idea is to have k steps Gibbs sampling and k equal to 1 until convergence. Typically, k is 1 means for 1 times this process is carried out. This applies to the gradient for one sample, and doing k time sampling as follows. At the time t sampling, okay, so this is h t means sampling at time t. H is our hidden unit variables, and probability of h condition on x at the same time x t, and then sampling of xt plus 1 is approximated through probability of x condition on ht. Okay, so it is like sampling hidden variable values h from sampling visible variables x at time t. All right, at time t we are sampling the hidden variables, this h hidden variable values are this h, and what are sample visible variables x are sample visible variables. We use these just sampling hidden variables h to generate the visible variables x data again because this is learning process means it is done for n number of times until it converges means there is no further improvement. So uh, until that time this process is repeated, and this approximation of the equation given in 28 like this one, probability of hi equal to 1 condition on x naught, and this x naught j sub j minus p of hi equal to 1 condition on xk. Okay, so for various I, J, and K values, this you are computing values through that equation. And here, this is illustration. This H naught, H1, H infinite N, X naught, X1, Xn. And if you see here, this is X, J, H, I. This is X, J, H, I at zeroth time. Okay, time t naught, time 0. Okay, at time 1, uh, which is xjh1 at time 1, like that uh, the same is performed till time n. Okay, xjhi till time n. And this is the one-step contrastive divergence algorithm, which is used for training the RBM, restricted Boltzmann machine. Here, what is the data sample, L data samples in set L, X1, X2, XL. These are data samples, data set. In this data set, we have input values X1 to XL, and this input number, latent variables, uh, and learning rate. Latent variables are again those variables which are found in hidden units. All right, those variables, and there is a learning rate alpha. What will be the output? Output is learned weight matrix W, bias vectors B and C. We know that X is to be multiplied with B and H to be multiplied with C. Those are bias vectors, and that is the output. And also this weight matrix, weights are only learned during learning process in any deep learning model. It is the weight that is learned during the training process. And then this is the first initialization step W. To some numbers, random numbers. W belong to some random numbers. Some random initialization is performed for W, B, and C randomly. And then for each this x1, x2 uh, belong to L. This L set L. What is done is this sampling is done performed x naught. You are initializing xk to x naught, and then probability of h condition on x naught is h naught. X1 is probability of x condition on h naught is x1. And then this gradients are updated through that derivatives. Those derivative equations are given earlier, right? Using those derivative equations, gradients are upgraded, and finally the parameters are updated. What are the parameters? Weights, bias, and this constant. Means bias constant for hidden, bias constant for visible layer, that is updated. So this is nothing but the training of RBM. Okay, this is sample distribution equations are given, and there are other algorithms for training RBM. One of other algorithm, the standard algorithm is that uh, whatever we studied, this one. This is the standard algorithm for RBM training, which is contrastive divergence algorithm. Besides this standard algorithm, there are some other algorithms which are based on generative model, GANs. Generative models. Generative models is the topic of Unit 5, which is about the model generating the data. Okay, so through that also this Boltzmann machine can be trained through generative models. This is um, about training RBMs. Any doubt? Next topic is deep Boltzmann machine. A deep Boltzmann machine. Uh, we studied restricted Boltzmann machine. Restricted Boltzmann machine is the one. Okay, 1 minute. This uh, deep Boltzmann machine has got more layers. RBM has got only 2 layers. Look at here. This is the figure for deep Boltzmann machine, where we find that there are um, nodes in the visible layer or input layer. This is visible or input layer, and it is followed by this one is followed by hidden n number of hidden layers. You can have n number of hidden layers. This is hidden layer 1, hidden layer 2, hidden layer 3. Whenever you just increase the number of hidden layers, essentially it turns out to be DBM. RBM only 2 layers. 2 layers only, not more than 2 layers. What is DBM? DBM has got more than 2 layers, 3 layers, 4 layers. These are the important points of this DBM. It's unsupervised probabilistic generative model with entirely undirected connections between the layers. See, these connections are uh, undirected, and this contains visible units and multiple layers of hidden units. In RBM, we have only one layer of hidden unit. In this visible unit 1 and hidden layer 1, RBM. Whereas in DBM, visible unit only 1, means one layer of visible units and followed by multiple layers of hidden units. Like RBM, there are no intra layer connections. You cannot have connections in this manner. You can have connection only in this manner. uh, Network of symmetrically connected stochastic binary units. We know that RBM is stochastic. Stochastic in the sense that it is not fixed. Uh, things are not fixed in RBM. Likewise, DBM also it's stochastic. DBM can be organized as bipartite graph because you don't have any intra-layer connection. You have only interlayer connection like this. It is modeled as a bipartite graph. Units within layers are independent of each other but dependent on neighboring layers. These two are independent. However, this is dependent on this one and this one. They are dependent on units uh, in the neighboring layers but not within the layer. Learning is made efficient by layer pre-training. Here, how learning is performed in DBM. DBM has got multiple hidden layers. Here, the learning can be made efficient by pre-training this network layer by layer. You're training this, and then this. Like that, you perform a training. After learning the binary features in each layer, DBM is fine-tuned by backpropagation. This also functions in two-phase, forward phase and backward phase. In this backward phase, this backpropagation uh, algorithm is implemented for the model to learn. Then what is the difference between, okay, there is a other category of networks known as deep belief network. And then there is a category of network known as deep Boltzmann machine. What are the differences? DBN and DBM are unsupervised probabilistic generative graphical model. consisting of stacked of RBM. Both deep belief network and deep Boltzmann machine both has got RBMs, means this visible and hidden. Whereas in DBN and DBM you have multiple hidden, and DBN and DBM are unsupervised probabilistic generative graphical models. Both DBN and DBM are used to identify latent features. Latent features are those that are hidden in the input variables which are used to represent input for the representation of input. This both the DBN and DBM performs inference and parameter learning efficiently using greedy layer-wise training. All right, layer-wise training means not training the entire model at once. Entire model at once is how output layer back to uh, its preceding layer, then back to its preceding layer, like that until it reaches the input layer, and then updating the weights based on uh, all the values. That is a one-time training. Whereas greedy layer-wise pre-training is you train this to, then you train this to, like that, layer-wise, and then both DBN and DBM use a large set of unlabeled data for pre-training, okay, in an unsupervised manner. What does it do? It finds good set of parameters for the new model and then apply this discriminative fine tuning on. This is deep Boltzmann machine. This is deep belief network. Excuse me. Okay, we'll continue tomorrow.